Good afternoon, everyone. I'm Michele Marelli, and I will present the first topic of this afternoon. And thank you all for being here, and you're welcome. So what I will discuss about is the use of one software, one CFD software called ParticleWorks, based on the moving particle simulation method, to analyze the lubrication and the cooling of mechanical components in large pumps. So I will explain you what type of system we want to analyze, what are the features of this new approach, and I will explain you how this approach can give you insights and design indication in order to improve the lubrication of these components. So the agenda for this afternoon is as following. So at the beginning, I will introduce some motivation and also give you references about the topic and why lubrication is this important in this kind of system. The references will include some papers that we refer to as well at the end of our presentation when we compare our simulation with some experimental results. Then I will discuss briefly on the type and the typology of lubrication solutions that are present in this kind of systems, and I will go into detail about some of these approaches that we can simulate with the software very easily. I will briefly explain you as well the moving particle simulation methodology and the software that we use, and why it enables a very fast simulation process in this kind of system as compared to more conventional but less easy to apply softwares. And then we will see an example and a comparison of one of these digital models with an experimental setup that, again, we will give some additional information later. And we will conclude with a summary of everything we said. So the motivation are easily explained. The lubrication of mechanical elements, especially bearings, in this kind of centrifugal pump is key. It's key to guarantee that bearings don't fail and don't fail too early. So there are a lot of papers in this direction suggesting that most of the failures for bearings can be attributed to lubrication, so lack of lubrication. And actually, 2/3 of rolling bearings also fail prematurely. So it's very important to analyze and promote the lubrication of bearings in this kind of system. There are different strategies. You can see here highlighted 2 of them, of the 4 strategies, the most important one. And the 2 that we highlight here are the one that we will analyze with the software. So we can have grease lubrication, oil bath lubrication, or splashing lubrication through disc or a ring, and also oil mist lubrication. So going into detail about the second and the third approaches, we will see these approaches and what are the differences. But before going there, I want just to give you the references of the work and also the geometry that we will work on. So the geometry will actually be based on the paper, on the studies from Simon Bradshaw when he was working in Sulzer pumps. So we do use again the technical drawings, and also we try to refer to the experimental setup that is studied back in 2014. Explaining you now the type of solution, of lubrication solution. We do have 2 approaches. One is the oil bath, so-called oil bath approach, where the oil level is reaches actually the best point, the the best lubricating point that is in the middle of the lowest bearings, and this is the ideal solution and the ideal case. It's used in low RPM conditions since the very high volume of oil can, of course, cause some churning losses. When we move to faster systems, the amount of oil needs to be decreased. Otherwise, there are too many churning losses and splashing losses due to the interaction between the rotating elements and the oil bath. Because of that, there are other solutions to favor the lubrication of the bearings area, and this approach is then based on oil ring or disc splashing. So let's explain in detail what this method is about. So the idea is to have some elements that gets in contact, some rotating elements that gets in contact with the oil bath, and due to the splashing that occurs after the interaction, we can have some directional flow, also helped by and guided by some channels, some specifically designed channels, towards the bearing area. So in one approach, a disc that is solidly moving together with the shaft can be used, but there are also other opportunities. For instance, the ring approach uses a ring that can move freely with 6 degrees of freedoms, both with vibrations and also translationally, both with conical vibration and translatory vibration. So in this case, the ring it's not fixed as in the disc one. So here we have another section of the same design and concept. As you can see, there are now highlighted also the channels that can collect oil splashed from the ring in this case, and you can imagine that due to the complexity of the flow and the deformation, the high deformation of the fluid domain that results from the interaction between the solid and the fluid itself, the splashing phenomena is very difficult to analyze with conventional CFD methodologies. Moreover, when we also, let's say, take into account the fact that the ring has to be modeled at the same time, together with the fluid phase, and the interaction between the ring and the fluid needs to be accounted. Of course, traditional CFD and methods really struggle in this direction. So that's why we propose now to use particle works, novel technique that is based on the particle-based computational fluid dynamics. So in this case, basically, we are talking about a technique that doesn't require the generation of any mesh. Rather, the fluid domain is discretized at the beginning of the simulation in particles, and we follow these particles during the solution, applying the usual Navier-Stokes equation and usual CFD equation. So this is a Lagrangian method that, again, uses a dynamic mesh, if you wish, to solve the same equation as in conventional CFD. Because of this, it's very suitable whenever we have problems dealing with large deformation of the fluid domain and also, let's say, free surface flows or liquid jets, for instance. And it's also very suitable whenever we have a lot of rotating elements or moving elements, because the fact that we don't need to care about the mesh generation or the mesh adaptation can really speed up the simulation process. So again, just repeating a little bit, conventionally we have this kind of picture where we generate a mesh with nodes and we solve onto these nodes the CFD equation, let's say. In the MPS method, we have computational nodes only where needed, and we follow these nodes, for instance, during a splashing phenomena, in a Lagrangian in a Lagrangian way. Okay, and it's again ideal because we have the computational nodes only where needed and not everywhere, and we can follow our fluid very accurately. So the simulation steps are here listed, and also the simulation time is represented. Since the mesh generation step is not present anymore, we can start our simulation directly with the settings, the boundary conditions. So in Particle Works, the preparation of the CAD is very easy and fast. We don't have to clean or prepare any mesh again. And we can set up straight away our numerical setup. Moreover, due to the fact that the algorithm behind Particle Works is easily parallelizable, we can take advantage of GPUs, so graphic cards, that are very good whenever we have problems that can be parallelized. Okay, so as compared to conventional CPUs, we can have another speed up of our simulation process thanks to this approach and this feature. The application of Particle Works are also in line with the feature that I already mentioned. The first and most important application was, of course, in gearboxes and transmissions to analyze the splashing and lubrication of these systems, but also the lubrication of bearings. In this case, with grease, is also possible. So we can also have non-Newtonian behaviors in our fluid. The sloshing in tanks is also a common application, as well as the lubrication and the cooling of traditional and electric motors. This aspect and this, let's say, application is increasingly important, of course, for the transition that we are into right now, and especially because the thermal capabilities of Particle Works are also very, very important and they capture very well the phenomena, the cooling phenomena. We do have also other less conventional topics that we can deal with, for instance, hydroturbines, but also mixers and high viscous flows in general. This just to give you an overview of the fields of application that are actually very, very different, and they are expanding month after month, let's say. Okay, going back to our centrifugal pump and on the main, let's say, simulation that we will discuss. As I mentioned, the study that we worked on, so our simulation is based on this study from Simon Bradshaw, in which basically Simon and its co-worker try to analyze the lubrication, the possibility to collect some oil with a system that is schematized here at different RPM and different oil levels. So we will go into detail about the objective of this study and also the comparison with our simulation. But the idea is that we took and we try to replicate in the best way possible the technical drawing, and we recreated a, let's say, digital model of the same system to have a comparison, the best comparison we could between the experimental and the simulation setup. Here there is a scheme of the setup in Particle Works and also the geometrical elements that we included in this modeling. So we do have a shaft, some bearings, very schematized and reported here in a very simplified way, and then also an housing all around. and these three elements were assigned to a no-slip wall boundary condition. So the rotation of every one of these elements, or let's say the kinematic law, were predetermined, and they were set up by us. Differently, the oil ring element, as you can see, is assigned to the solid material that is possible to assign in particle works. This means that the oil ring is discretized with particles in the same way the fluid is, and this aspect, the fact that we discretize for this solid material, enables the coupling between the fluid and the solid. So basically, on this element, we didn't include any kinematic law, but we just let it interact with the surrounding elements. And then we have the oil volume down here that was initialized with a filling plane. So we just needed to define a point and a plane, and below that plane, the oil was initialized. We could also have used a solid, the fluid volume from the CAD, but Particle Works also enables this option of the filling plane that in some cases is much easier. The CAD and the casing also had a collection channel, as you can see. So there were actually two collection channels symmetric to each other to feed the two, say, the two bearings areas. And we will see in the next simulation, actually in the next animation, how this feeding channel was populated by oil after the splashing. So here you see the results, some results from Particle Works. As you can see, the ring is interacting with the shaft, is moving due to this interaction and the grip between the two, and oil flows because of the interaction between the ring and itself, and goes to the channel, only one channel. And as you can see in the other animation, we also do see some oil dripping down in the bearings area. So exactly as expected. So I will just replay for a couple of seconds the two videos if you didn't catch every detail. Okay. We also wanted to monitor on a quantitative way, let's say, the flow rate going through the channel, but also the oil amount that was collected in the bearing area. As you can see here, we have two bearings. One was named ring, in proximity of the ring, and one in the anti-ring configuration. From literature, we knew that due to the rotation, due to the asymmetry in the rotation, actually only one of these channels would have been populated. And that's exactly what we saw. In fact, we can see that there is a flow rate going through the anti-ring bearings area, while in the other case, we actually don't see, in the other channel, we don't see any flow. And also the oil amount in the area can be monitored in a very easy way in the software, and as you can see, there is the same asymmetry between the two areas. So we started to see some behaviors that were very physical, very representative of the experimental setup. We wanted to investigate further how close we were in terms of numbers and trend, and that's why we, again, referring to the same paper, we tried to analyze if we could capture the same trends in terms of oil flow rate that were observed experimentally. So the idea experimentally was to change the rotational speed of the shaft as well as the oil level, and understand how the lubrication of the system changed. We did basically the same. We selected one working point, and we actually were able to replicate some trends, meaning that with a different submergence, we were able to increase the oil collection in the channel, as also reported in the paper. So in blue, we have one submergence level, and in orange, we have an increased submergence level. So we were very happy because we could see some correlation between the experimental setup and the digital twin of this system, let's say. And we, of course, we actually know that due to the fact that the geometry is not 100% representative, and also there were some assumptions, strong assumption on the material properties of the ring and the shaft. Of course, we cannot say that we got 100% the same results, but at least we got the same trend, we got the same order of magnitude of the flows, and let's say for an initial test, we were very, very happy with it and with the correlation we observed. So in conclusion, we talked today about the strategy of splash lubrication in centrifugal pumps, and I tried to highlight it how and why ParticleWorks can be a key software to improve the lubrication of this kind of system. As I mentioned, another important point, it's not only feasibility in terms of software, but also feasibility in terms of simulation time and, let's say, development time. And as I mentioned, with ParticleWorks, we can fit our simulation process inside the very demanding design, let's say, design schedule and design or production timing. We visualized the oil distribution, and we gave some quantitative evaluation of the flow rate and the lubrication efficiency. And we also showed how we could correlate the results we got with some experimental setup. I hope I was clear, and I will just finish my simulation, my presentation with a simulation, or actually a video showing the same simulation here with a nice rendering that is now possible also thanks to a new feature of ParticleWorks. And I will also include the detail about where you can find some more information about ParticleWorks. There is the link here, particleworkseurope.com. You can also find some test cases, some more information videos. So if you are interested, please check it out. And there is also my email if you want to know more about the software or the possibilities. Thank you all for listening, and I will check if there are any questions.
No, we have no question at the moment.
Okay, perfect. Then I think I will leave the floor to Rainer, and yeah, I will be happy to answer my question in case later. Thank you.
Okay, hello everyone. I hope you can hear me. Yeah, thank you for everyone that is attending us today and is listening to us. I am Rainer from CFX Berlin, and today I will talk about rotary pumps the best practice to pursue the highest possible efficiency. So my presentation will give you a brief introduction about our approach to simulate those types of machines. And yeah, let's have a look at the agenda. So my presentation will cover 3 parts. First of all, there's just a short introduction about our company, CFX Berlin. And then we will move on and I give you some information about the modeling background to our approach. And then we will have a look at some simulation examples as well in the industry, and also some free geometries for different machine types, which I'm able to share. And my presentation will close with a short live demonstration where I can show you the workflow from scratch, where we will set up a simulation for a 3D lobe pump. Okay, we at CFX Berlin, we are doing simulation well over 20 years now. And over the time, we became an ANSYS Elite channel partner, and we are also channel partners of MTech and EngineSoft. As such, we provide solutions for, or primarily for fluid mechanics and thermodynamics, also structural mechanics, electromagnetics, and coupled physics. Our company, we are active in the business areas, so we sell ANSYS, Twin Mesh, Flownics, and Particle Works. And also for our services or for the application the customer needs, we provide, for example, hardware, training, or consulting services. And last but not least, we have a small research and development department. So the topics I mentioned, the software, so all ANSYS products, and also Twin Mesh, which is our own development, Flownex, and Particle Works. This software you can get directly from us if you are from the German-speaking parts in Europe. Okay, let's move on to our approach to simulate the rotary machines, or to be more specific, positive displacement machines. Our approach is called Twin Mesh. And as I said, this is our own development. And the idea is that we have a tailored workflow for this specific machine type. So here you can see the component Twin Mesh, which is a mesh generation software for positive displacement machines. And it works seamlessly with ANSYS products. That means we generate the working chamber of those machines in Twin Mesh, and then we can combine them with, for example, the stator volume is meshed in ANSYS meshing. Then we move on to the preprocessor, which is CFX Pre, for example. And then at the end of the workflow, we have our simulation results. And yeah, that is the idea. And since Twin Mesh is our own development, we are able to distribute it internationally. So this was actually the slide I was referring to. And thus we have, as you can see, at the moment, customers from all over the world. So from the industry and also from universities, for example, which are using our approach at the moment. Twin Mesh at the moment supports different machine types. So above you can see different pump types. The most common are external or internal gear pumps, G-rotor pumps, or lobe pumps. And we have also, or we are also supporting the compressor types, for example, screw compressor, scroll compressor, and so on. Then what are the challenges and why do we need a specific software to perform simulations for those machines? So first of all, the positive displacement machines, as you can see on the right-hand side, they have a very complex geometry. So in this case, this is a screw compressor. And for those complex geometries, the meshing would be challenging in any case. But in addition, the rotors are spinning, so we have a continuous change of the fluid volume, which we have to model in some way. Also, if you look between rotors and housing, there are basically clearances everywhere. So we have the intermesh clearance between the two rotors, and also radial clearances and axial clearances between rotors and housing. Also, the physics in those machines are quite challenging. For example, if you have a pump, you can have something like cavitation, which refers to a multi-phase problem. Or for compressors, you have a compressible gas, or depending on your operating point, you have to deal with real gas properties and so on. So all those aspects, they lead to specific meshing requirements. So you are able to do reliable CFD analysis. Okay, the statement on this slide, it can be summarized real quick. As I said, we have specific meshing requirements for those machines, and especially if you look at the clearance flow. Typically, the clearances are very tight, and you have to capture those tight volumes with a mesh. And as you can see, from experience, we know that a feasible mesh should fulfill certain criteria. For example, if you look at the mesh quality, the element angle, the volume change, and the aspect ratio of the cell, they should lie within a certain threshold. And also the best way or the most efficient way to capture the clearances in those machines is to use hexahedral elements. There are several approaches you could take to deal with this kind of simulation. For example, overlapping meshes or remeshing or handmade hexahedral grids. I will not go further into detail about the different approaches, but they have something in common. They have some disadvantages. So they refer either to very large models or they lack in accuracy when we are speaking about, for example, to capture the leakage flow through the clearances. And our idea now is to combine all the advantages but neglect the disadvantages in the same way. And this is what Twin Mesh should provide. It provides reliable results, but also your workflow is really fast because it's an automated workflow and you get hexahedral grids automatically. So the idea is, if we look at this lobe pump here, we discretize the working chamber with the grids generated in Twin Mesh. Then we combine them with the rest of the machine, which is basically the stator part. Here you can create a mesh in any meshing software you want, as long as it is compatible to your solver. And as you can see, then we perform the simulation on those meshes we created, and we get all the flow quantities, and we can use all physical models which are present in ANSYS. Then we have a look at some simulation examples of rotating PD machines. So first of all, some examples from the industry. So those are reference customers where I am able to share the information with you. So for example, Hugo Vogelsang, they use our approach and they did a design optimization with Twin Mesh. So starting from an initial design, then they changed the stator parts of the machine in order to get a better efficiency. And then, of course, they end up with an optimized design. Next example is company Bosch. They did an analysis for a waste heat recovery system. So what you can see on the right-hand side here, this is a scroll expander. So high pressure, the gas is entering the expander, and then the heat is converted into mechanical energy. And they did a publication on this matter, and they showed that the results are reliable and in good accordance with their measurements. Also, a scroll machine type, this time it's a compressor. There's also a publication from the company Danfoss, where they showed the methodology how to capture the simulation of this machine. And since they use this approach, they can say that they save over 60% of their time using twin mesh and ANSYS CFX compared to other approaches. Another example, this time it's a pump, a vane pump. On the right-hand side, you can see the underlying mesh where the simulation is performed on. And on the left-hand side, there's an animation, or actually it's a volume rendering of the velocity field. And depending on when the chamber passes or when the vane passes the control edge, you can see that because of the pressure buildup, there is something like a bit of an overcompression, and you have this jet coming out of the chamber. This could be the basis of an optimization problem where you design the pump or the chamber volumes in a way that this does not happen. Then we see a filling process of an external gear pump. So this is actually a multi-phase simulation where at the start the pump is empty, and then we inject water into the pump, and you can see over time how the pump is filling up. So what we get from the simulation is time and space resolved flow quantities wherever you want to look in the pump. Yeah, just another example. This time it's a 3D lobe pump with twisted rotors, and we see that we can visualize and evaluate the velocity field or every other flow quantity on different cross sections within the machine. And if you look at the bottom right, the top right visualization, here we see velocity vectors which are on a plane within the axial clearance. So although the clearance is very tight, we are able to calculate the flow field within those clearances. Then another visualization is internal gear pump. This time it is a single phase simulation, so it's filled with a high viscous fluid. And then we just inject something like a tracer to the inlet coming from the left. And then we can see the distribution of the tracer within the pump. So it goes through the working chamber, and finally it's ejected at the discharge port. And of course, the movement of the tracer is based on the flow field which is calculated. So now we saw a lot of animations, but of course we can go more into detail. We can do a distinct analysis of desired flow quantities. For example, here this was a gap a gap study where we changed the clearance sizes. So we have 3 different sizes from 40 micron to 80 micron. And for all those cases, we run the simulation, and we had a look at the flow rate, the chamber pressure, and vapor volume. So there is cavitation involved. And as expected, when we decrease the clearance size, the flow rate is increasing, and we can quantify how much it is increasing. So you get an idea how sensitive your pump will react to those changes. Could be important for manufacturing tolerances, for example. And also with tighter clearances, we see that the chamber pressure at some rotor position is increasing, and you also see effects like an overcompression, which is happening, and also increasing vapor volume. So that means the tighter the clearances are in this case, the more pronounced cavitation could be. Then another example, we did this simulation. This is a screw expander. We did this in collaboration with the Technical University of Dortmund in Germany. We calculated the flow field, and then we had the pressure volume diagram, or here it's pressure over rotation angle, and we compared this to experimental data. And we had a very good agreement between experiment and our calculation. So qualitatively, but also if you quantify the values, there are some deviations which you can explain. For example, in this case, the bearing leakage was not modeled, but overall, we could show that the approach is able to model what's happening in the machine very well. So now I showed you some examples and how the approach works, but I think it's best to exemplify it by having a short live demonstration. So the pump which you see here on the slide, this is a 3D lobe pump with twisted rotors, and I will just show you how to generate a mesh for this pump and how to set up a simulation for this. So let me minimize my presentation and I bring up the geometry. So now we are inside of ANSYS space claim, and you see the pump from the slide. Let me hide this for a moment. So we look into the working chamber. Of course, we see two rotors and the housing. And now the question is, how do we get meshes, especially for the working chamber, which is changing over time? So the first step is always to import the geometry to TwinMesh, and the only thing we will need in TwinMesh at this point is the rotor profile. So we need a 2D cross-section of our working chamber. So the most easy way to do it is just to select the curves which describe the rotor profile. You could copy them in a new construction sheet, for example, and just say save as, and you save it as an IGES file, and then you can import it. This is what I prepared. So this is the SpaceCam project. Here is the IGES file, which contains the curves you just saw. And now we open TwinMesh. So this is the starting screen. At the beginning, you can select what machine type you want to create the meshes for. We said we want to create meshes for a low pump. So we click it and then it is set for the project. And first step is we import those IGES curves. So now here they are. And in the next step, we tell the software what those curves are. So at the moment, TwinMesh doesn't know yet, is this a rotor or is this a stator? So what we have to do is we select the curve. If it consists of more than one segment, we can say select all connected curves. Oops. And we assign this to rotor wall curves, first rotor, and repeat this for the second rotor. Okay, so they changed the color. Now it's clear that those are rotor curves. In the next step, we just provide some basic geometry information. So in the structure tree, we can go to geometry, and we see that there is an entry for rotor 1 and 2. So for rotor 1, we provide some information. For example, we have 3 lobes, and we have a casing radius of 120 millimeters. we repeat this the same for the second rotor. We have 3 lobes and 100 millimeters casing radius. And also the center of rotation for the second rotor has to be shifted to the right. So we changed the X component to 180 millimeters. So as you can see, now we have described the rotor curves and also the casing curves by just entering the casing radius. If you should have something which deviates from a circle-shaped casing, then you can import separate curves the same way I did for the rotors. So in the next step, we check about the clearances. So if I zoom in here, we would expect to have the radial clearance here. But if I keep zooming in, you get the idea there is actually no clearances because in this geometry, the outer diameter of the rotor is the same as the housing diameter. So now you could either go back to your CAD geometry, or you can also fix this issue inside TwinMesh by, for example, applying just a small scaling factor to the rotors. So this is what we are going to do here. I go to rotor 1 and I do a geometry modification, and I say type of scaling is a normal scaling with the value of, for example, let's say 0.08 millimeters, so 80 microns. We enter the same for second rotor. If I zoom in now again, now we see that there actually is a clearance. We can also measure the clearance, and we see it's about the 80 microns, which we just specified. Okay, also in the intermesh clearance or at the intermesh zone, there is a clearance. That's good. That means now our geometry is well defined and we can generate the meshes for this. Maybe for you, it's also important to know exactly what the different clearances are. And there is the possibility in TwinMesh to evaluate clearance sizes in the machine. For example, let's say minimum housing clearance between housing and the first rotor. Now it calculates for all the different rotor positions. Here it's basically 80 microns everywhere. You could also say I want to have the profile gap in the intermesh zone. And here we say we are around 160 microns. So before you even generate any mesh, you already know what the clearances are. Okay, then in the next step, we proceed with the mesh generation. Let me turn on the node distribution. So there are different strategies for different machine types. But yeah, basically you are good to go with the default settings, which means for a low pump, we use the so-called outer fix. That means we have the nodes placed on the casing curves, as you can see here. And you can set the global element size. You can decrease it, for example, here to 5 millimeters. Now more nodes are placed on the casing curve. And then in the next step, you would just say generate current mesh. In the first step, yeah, something like an interface is generated between the rotors. This is the curve here. And then in the next step, the mesh is generated for this rotor position. So this, I think this looks already good, but typically, yeah, you can do it a bit better. For example, what we want to capture with our simulation is something like the influence of the boundary layer. And what we do for this is, yeah, to apply a higher mesh resolution at the wall. So that means at the housing wall here on the left, but also on the rotor curve. So the goal is to have smaller elements on the rotors, for example. Of course, we won't do this by hand. We can specify the first element height directly in the mesh settings. So first element height on the rotor side and also on the housing side, let's say 50 microns. And then we are going to need more elements in the radial direction. So I say generate mesh once more. And now we see the result. we have a so-called inflation layer towards the walls in the radial direction, and a bit coarse resolution in the zone in the middle here. But we already have a very good mesh. So a very good mesh, we want to check if it's really good, and this we do by visualizing the mesh quality criteria. So what you are seeing right now is a contour plot about the mesh quality regarding the minimum element angle. So twin mesh also shows us where this occurs. So this is the element down here. If I would change it, you will see that the mesh quality is adapting. So if there would be a problem, you could directly see where is the problem, and you could change the settings and then eventually get the good mesh quality you want. So other quality criteria are, for example, the aspect ratios of the cells. We see they are around almost 1400. This is very good for CFX. If you are using Fluent, for example, you might want to get a smaller value, then you would have to put a bit more nodes in this gap. And as you can see, there are also other criteria I won't discuss in this webinar, but the goal is before you generate the meshes for the remaining rotor positions, you first check if the quality is sufficient. Yeah, speaking of the other rotor positions, as you can see, if I scroll through all the rotor positions possible over one pitch, there are no meshes yet. So the next step would be that you say generate all meshes, and then twin mesh will generate the meshes in the background. This can be done in parallel. So if you have more than one CPU core, which you typically have nowadays, you can use up to 16 cores to generate the meshes, which will give you a good speed up. So, but to give you an idea, for this machine, this might take up to maybe 15 minutes to generate all the meshes. And because we don't want to wait for this time, I will show you the finished project for this machine. So here we have the same geometry, but here every rotor position has now a mesh. And the final quality check would be that we say again, show me the quality. And as you can see on the left side, this chart or this table, twin mesh calculates the worst element angles for all 120 rotor positions. And as you can see, there is no value worse than 20 degrees. Actually, it seems like, it's about 40 to 50 degrees, which is, I think, perfect. So at this point, we would say, okay, the mesh quality is good, and we will proceed with the simulation setup. So if you remember, of course, our geometry is not two-dimensional, but three-dimensional. So we have to specify also the length of the rotor in the axial direction. And this is something which can be done in twin mesh, let's say on the fly. If we look at the 3D view of the meshes, you just have to specify the length in the axial direction. For example, you can change the value, then the mesh immediately adapts. Let's put it back to the actual value. And the same goes for the twist or the wrap angle. In this case, it's about, it's 60 degrees. You could also change the value to another one, and then also the mesh adapts immediately, and you can, re-export the grids for the use in CFX or Fluent, for example. Okay, then at the moment, the current version of twin mesh is meant to be used primarily with CFX, and this will change in the next release, where we also support this tailored workflow for Fluent. But the idea is to have a template-based solution for CFX or Fluent, where we combine this grids to the grid which comes from ANSYS meshing, so the stator grid. So just to show you what I mean. So this is the stator of our pump, and I prepared a mesh in ANSYS meshing. And as you can see, we have different named selections here on the left-hand side to describe all the phases of our mesh. So for example, we have an outlet. This is down here. Then on the opposite side, we have the inlet. We have stator walls and also phases which define the interface between rotating and stationary parts. And now the trick is we just provide those name selections to TwinMesh. This is what you see in the fields here. For example, inlet location. Let me bring this up. You can set this is the phase which has the name inlet. We say accept. And you do this for all the other name selections as well. Then we can specify boundary conditions, so revolution speed, inlet pressure, inlet temperature, and outlet pressure, and also some solver definitions. And once you have done this, you say export. Oh, first, let me check. Yes, here we see open ANSYS CFX-PRE is set to yes. That means after the export of the grid data, CFX-PRE is opening automatically and is assembling the setup for us. So this is the last step we do. Yes, we have to overwrite the existing files. So now it's done. And as you can see, CFX-PRE will now open. And in the background, it will load the grids from TwinMesh for the initial position and also the mesh coming from ANSYS meshing. And it will assemble the setup for us because TwinMesh knows what machine type this is. We specified the operating point, and yeah, once it's finished, we see that the model is imported. If you are familiar with CFX, this setup might be familiar to you. So we have all the meshes on the top, then we have the domains, so rotating domains and the stator domain, and all the boundary conditions which we need to run the simulation. So this was just a quick overview for you, not to understand all the details, but to so that you can grasp the idea how to go from CAD geometry into the finished simulation setup. And this is actually a ready to run setup where you could now start the solver and perform the simulation run. Of course, all the details of those setups and what you can set in TwinMesh, you would learn in a professional training. Yeah, I hope this was interesting for you. I will close my presentation with just one more slide. If you need more information about the TwinMesh approach for positive displacement machines, you can go to our website, twinmesh.com. There you will find, for example, some publications, papers, or success stories from customers. This is you can find on our blog, and also just more examples where you can browse through. Okay, at this point, I will end my presentation and I would hand over to my colleague. If there are any questions, if we have time, we can try to answer them now. But afterwards, if you have any questions, you can write me an email to rainer.andres@cfx-berlin.de. Okay, yeah, let's see if we have any questions. If not, my colleague Bastian will take over and present the next topic to you. Thank you very much.
Hello, this is Bastian Schöneberg from CFX Berlin. For anyone who has just joined yet, we distribute ANSYS, Twin Mesh, Flownex, and Particle Works, and give trainings and support for the software. We also offer consulting and simulation services, which means that we use the software every day for solving engineering problems, so we can support our customers with first-hand experience. In the next 30 minutes, I would like to give you an insight into the modern design of centrifugal pumps, which means that we are using computer-aided engineering tools to accomplish this task. First of all, we have a certain task for our pump, the duty conditions. The design process now involves all the steps needed to create a final prototype. If there is no existing similar pump, we have to start from scratch with a preliminary design. After that, we need to create a CAD geometry, which is the basis for numerical analysis. Based on the results of this analysis, we can try to optimize our design. Of course, there are different aspects of numerical analysis. From a simulation perspective, these are the main fields of interest. An electromagnetic field calculation aims on designing the pump drive. Structural analysis tries to ensure that the parts can handle the material stresses occurring in operation. We are focusing here on the flow analysis, which tells us what is happening on the fluid side. In the present case, the drive is provided by a supplier. It is an alternating current induction motor, which is a common choice for pumping applications. It also means that our pump will operate on fixed speed conditions. So this is our first important design parameter. What else do we need to know? Density of fluid, volume flow rate, and pressure difference, which is the static head. The operating point for the pump depends on the system's pressure loss curve. If you don't know this curve, you can use a flow network tool to calculate it. The Flownex software you have seen earlier today can do this job. So now that we know the duty conditions, we can continue with the preliminary design of the pump. Many companies use own Excel sheets or old Fortran programs to do this. Here you can see a simple example, which I often use to estimate the impeller size needed. Those tools have the advantage that they are tailored to the needs of the company, but are often not very up to date. Especially the output of geometry data can be a problem. Specialized software can be an alternative here. Well-known programs are CF Turbo from Germany, Concepts and ERC from the US, or ANSYS Vista CPD from London. They all have a good connection to the major CAD systems and analysis tools. They just differ in the design options you have available to reflect the needs of your pumping application. You know that a machine for pumping wastewater has other design requirements than a pump for corrosive chemicals, for example. Here I used the centrifugal pump design software Vista CPD by ANSYS. It is part of the product ANSYS Blade Modeler. It's based on classic analytic design and efficiency correlations. Using that, you can calculate the meridional contour of the flow channel, as well as the blade angles and the volute shape. Vista CPD outputs the design as a blade modeler geometry. And this blade modeler is a special tool for the creation of impeller designs that are ready to use for the analysis workflow in ANSYS Workbench. Here you can see some examples of possible turbomachinery types and shapes. You can easily modify the design you have just created in Vista CPD because the geometry is parameterized. And that, of course, is very important for later optimizations. It also provides an output for ANSYS TurboGrid, which is the next step here. So computational fluid dynamics software works with finite volumes. So of course, before we can analyze the flow, we have to create a computational mesh. The workflow here makes it very easy for us to do this. And this TurboGrid automatically creates high quality meshes for impeller geometries. Basically, we only have to adjust the element sizes if needed. This approach is also very robust to geometry changes. For the other regions around the impeller, we normally use unstructured meshes. ANSYS meshing is the general purpose grid generator in ANSYS Workbench. It can create meshes for all types of geometry and offers tools for handling problematic geometry and small features also. So once we have a mesh for impeller and casing, we can continue with the flow analysis. Here we used ANSYS CFD. That's a leading CFD code for turbomachinery. It's a general purpose CFD solver, meaning that you can calculate flow in a wide range of applications. Plus, it has sophisticated tools and solution methods for rotating machinery that help us in accurately predicting the performance of our pump. So how does it work? First, we set up the case using the free turbo mode, which guides us through the specification of physics and offers typical boundary condition combinations. Next, we start the solution process. This can be on our local computer or on a dedicated compute cluster in our network, or even in the cloud. Here you can monitor the solution and check the numerical quality. When the calculation has finished, we can proceed with the evaluation of the results. Again, the turbo mode helps us in quickly creating typical plots and performance data output. And this is how the final workflow looks like in ANSYS Workbench. So every box reflects a step in the design process. As you can see, we added connections from those boxes to the parameters section in the bottom area. Input parameters can define boundary conditions as well as geometry. Output parameters can be any result of our calculation. One way to use this parameterization is to calculate the speed line of the pump. In the table, every line represents a design point, which is a single operating point defined by flow rate here. After performing this automated parameter study, you can plot the output parameters over the input parameters. So in this example, the chart shows the static head of our pump over volume flow rate. Another very interesting aspect is the modification of the geometry. We can easily calculate different designs with a minimum of user interactions. So here I decided to widen the impeller eye a bit to improve the suction behavior. So the red curve was the initial design provided by Vista CPD, and the blue curve here is the new meridional contour I adjusted here. I also adjusted the blade angles a little bit to compensate for the larger cross-sectional area. So again, here the red curve is the first design, the initial design, and here the blue curves are the new blade angles. And here are the results of those two modifications. Static head reduced, and the required net positive suction head was improved, at least for the best efficiency point, but not for off design conditions, as you see here. So the orange line was the initial design. These modifications go hand in hand with higher losses, as we can see here. Static efficiency, just decreases here. And an experienced pump engineer can often create optimal designs with such a procedure, but sometimes this is simple trial and error. So why don't we use an algorithm for this kind of modification? We can connect an optimization tool to the parameter section, namely ANSYS Design Explorer or more advanced ANSYS OptiSlang. So this is the box down here. There are two main optimization approaches. The first one creates a response surface of selected output parameters over input parameters, and then tries to find an optimum on this surface here. The second approach uses direct optimization, which means that every design point is a CFD calculation. When deciding what approach to use, we should know about the specific optimization challenges in CFD. First, we have long calculation runtimes, which makes an optimization on a response surface a good choice. On the other hand, we will most likely produce some invalid designs, especially when covering the whole parameter space. Meta model algorithms are likely to fail when too many designs give no response. So this speaks for direct optimization. Also, normally we have a high parameter count, which heavily increases the number of designs we need to calculate for DOE or response surface. Furthermore, the highly nonlinear response of flow systems can make it difficult to calculate a smooth surface over the system response. And for that reason, we, not always, but often prefer the direct optimization approach here. And within this direct optimization, the evolutionary algorithms are very famous. The picture here shows the optimization history of a radial fan. So we started around here with the design, and then it takes about 300 calculations to gain a 5% improvement in efficiency. This whole process took us 3 days on 32 compute cores. So we finally reached our goal of a final prototype design. Up to now, the model we used was pretty simple. It is a good idea to refine the model to include more real-world details. For our pump, the first step is to take into account the leakage. Here we have an open impeller, which means we have a gap between the blade tip and the casing. To include this in our model, it is a simple mouse click in TurboGrid and roughly doubled calculation time. As expected, the blade tip has a big influence on the pump performance. So here a 4% gap reduces the static head by 25%. For closed impellers, like this one here, there are other sources of leakages. First, those pumps sometimes have pressure load reliefs, like this. This is an example mesh how to capture this. Those are used to reduce the axial force on the bearings and yeah, so increase lifetime and also decrease the friction in the bearings. Second, they also have gap leakage on the shroud side. And this can be included by adding the leakage path to the model. The picture shows a swept mesh generated in ANSYS meshing, which has a good resolution of the gap flow while keeping element count low, because we just have this extruded or swept mesh in circumferential direction. Another refinement aims at the resolution of unsteady flow behavior. In general, a rotating impeller inside a volute casing is not steady. It is periodically unsteady. The steady state assumption we used before is not able to capture such fluctuations. But even the predicted average values, this is the blue line here in the chart, can be wrong. So normally the steady state approach is okay at design conditions where we should have a blade attached flow. This example shows some worst case. Here the transient flow behavior is dominant over the whole speed line. So important to capture this, I think. Yes, as we include more details in our calculations, the computational runtimes increase. So what can we do about this? The first thing is to use efficient meshes. Hexahedral elements are generally preferred in turbomachinery because they allow for faster numerical solution and lower element count. This is especially true in small gaps as the blade tip shown here. So this is how TurboGrid handles this blade tip. We also have a fine resolution here. We should also carefully think about the accuracy we really need. Beside the mesh size, the selected models can have a great impact. Here we will compare different calculations of a radial blower with forward curved impellers. They are also called drum impellers. The second column of the table shows the deviations of the selected models from the measurements. As you can see, the transient rotor stator model is very accurate, but needs a long runtime. So here we should ask ourselves if the 10% offset of the frozen rotor model is maybe also okay for an optimization. And this will allow us to calculate an operating point or a design in 2 hours instead of 3 days. So this is a huge influence. Nevertheless, if you decide that high accuracy is needed, then you should really consider high performance computing. Here's a benchmark on a real live turbo case I did just last week. The hardware I used was this rack mounted machine in our server room. It has 4 compute nodes with 32 cores each. They are connected over a high-speed network, so we can use 128 cores overall. So this server can calculate 9 pump designs in the same time my workstation calculates only 1. So there can be a really big benefit. So that's basically from my side. I hope that I could give you some insights into the modern engineering workflow for centrifugal pumps. Let's see if there are some questions from the audience I can answer. Well, I don't see any, but if you have any further questions, don't hesitate to contact me. Here's my email address. Yeah, well, thank you very much. Then I would like to hand over.
Okay, thank you. At the moment, we now have a question on the chat. Okay, there is no question. Now there is the presentation of Ileana Vitale.
Good afternoon, everybody.
Yeah.
So good morning, good afternoon, everybody. I'm Ileana Vitale, and I'm the R&D leader for Ingersoll Rand for the division of centrifugal compressor. And today what I'm going to present are a few slides about the design and optimization of a centrifugal compressor stage and machine. Before we start, a very short introduction about Ingersoll Rand and the division I work for. That's the indicated here is the centrifugal compressor, but IR does a variety of different products. In the past year, IR merged with Gardner and Denver, and right now we are roughly 16,000 global employees with more than 300 years of experience and 13 manufacturing sites and 3 distribution centers. So this is very in short. What we're going to do today, I like to give a brief introduction about what process flow we can use while developing a new compressor, but in general, this process flow can be adopted to any kind of industrial equipment or in principle to any design process. I will then show a couple of design cases that we are typically to encounter during the development of a centrifugal compressor, giving a flavor of what could be the challenges that we have. And in particular, we'll focus over the optimization techniques. And also from that perspective, we are going to see few interesting perspectives. So let's start with what is a process flow for this particular environment. But as you can see, it's not really different from what you can face in any kind of design. The red block, it's really probably the ones where we have to put most of our attention in, as doing a very good problem definition and understanding it is all it really give us the opportunity to build up everything else. So during after a problem definition, you can imagine that the first step while you're designing something is to make some geometrical definition. So define your geometrical dimension. And even just at this level, you can start doing some optimization work. And then you can continue on adding, of course, all the physics you may be interested, adding more components, but also external requests. Nowadays, it's not unusual to get the request for components that are easily manufacturable, or for components that cost less than nothing, let me say this. So also in this respect, you can work with optimization tool, and you can go back and forth between a single component to a multi-component machine. A block that I have indicated here very schematically, but extremely important, is the multidisciplinary one. As inside here, I have actually imagined everything that can interact with your system. So while presenting that, I have mentioned I manage an R&D department, but personally I take care about the aerodynamic development. So everything we're going to see from now on is much more oriented to the performance generation of a compressor or the design of a centrifugal compressor from aerodynamic standpoint. But outside of my area, we also have the machinery, the manufacturing piece, the structural analysis piece, and so on. The interesting of the application of the mode frontier, so this is one of the optimizer available in nowadays, is that you can use it at any level. It's just a matter of how you would like to approach your problem. So again, your problem definition becomes the most important piece of it. So let's start looking into one of the challenges that we can face while designing a new centrifugal compressor. We can have a very simple, let's say, case, that's the stage design. And here we have, I have indicated a really simple example that is one of the components. It's just the design of an impeller and a diffuser with the characterization of the polytropic curves, so polytropic head and polytropic efficiency. This is one of the, let's say, most simplified topic you can have within the design of a centrifugal compressor. Is just the beginning, and then up to there, that you can add a collector, you can add seals, you can add volutes, and then you can start interacting from a stress point of view, and then you build the full machine. So the next case you can have is really the whole compressor. So you can see in this picture two typical products that we offer. And those are with inline coolers or with external coolers that include or not the possibility to have a volute within the study of a centrifugal stage or of a machine. And in the middle has been picked up for the following of the discussion and some of these slides I'm going to present, a two stages machine without the volute. So we are looking into a compressor style like the top left. And the characteristic of this compressor, especially for who does, CFD calculation, is that without a volute, we have a compressor. So with a collector, we have a compressor that has the characteristic to have stages that are can use symmetry. So you can reduce your compressor, actually your two stages machine, to a set of single sector per stage, and you can have the two of them running in the same simulation, connecting one to another one with a set of equations to transfer energy, to transfer the pressure drop and temperature and so on. So those are the main challenges. So you can go from the very single stage to the multi-stage machine. Let's look into details of what happened in this specific case into a CFX environment. So you can see we get from an external software, we get all the necessary information about the design of IGVs, of impellers, diffusers, and of the exit element. And we run a turbo grid mesh per each of them. Then we collect everything together into a design point, so a CFX block. And then from there, you can expand to a multi-point analysis or to a transient analysis. The multi-point is a feature that we have within CFX that is interesting, as you can run, launching just one simulation, you can run a compressor curve. And of course, you can then run a transient analysis or mix the two of them. So this is just a very quick overview about what can be within a CFX package when we study a compressor, a new compressor. Let's move on to the optimization strategies and make an easy remark about what an optimization looks like. When we talk about optimization, typically we have in mind making and finding the optimum of something. And in terms of engineering, is typical looking for a minimum or a maximum or something. What we're going to see is that while doing these activities using software like Mode Frontier, it is possible within the standard optimization to add some features like the methods, the surface response methods, to get a faster answer, and we will see that. But we can also benefit of some statistical analysis available as soon as you have done some optimization or some DOE analytics, with the particular scope to look for correlation between parameters and variables, and eventually decide how to refine your optimization or identify at early stage which are the most critical variables or parameters, or the ones that gives you more constraints. So all of that is the typical use of the optimizer and to correlate the softwares and packages available. But there is another way at which you can look at. If you think about when you run an optimization, at the end of the day, you get a design space explored. Typically, the typical use is to go with the design space and find, again, the minimum or maximum, but if you have set your variables of parameter in a certain way, your design space is actually telling you a lot more. And if you use the response surface methods, you can go investigate it for some particular things, getting the advantage that the response surface method allows you to get a faster response. And we're going to see some of the opportunity about that. So just a small deep look into the statistical analysis and the response surface methods. That's just a representation of what I've said. Top left, you can see an extract from a run where you can appreciate how much the variables and parameters that are involved in the calculation are impacting each other. The colors in this specific case, deeper they are, higher is the integration and the correlation between the element. In the specific case, we were investigating an impeller from a stress perspective, and we were looking to the weight and stress and try to understand how to best balance that with some geometrical dimension, ABC, and some other information we had available, like the deformation. The response phase method, on the other side, is an interesting method, but I always say it's also a tough one, and you have to be careful in how to use it. The main reason for that is because the response phase method is just creating a virtual representation of your design space. So it's said that the response phase methods are trained from an available database. So the more robust or the more with the more element your database is of real design, that can be either test cases or real analysis, the more your response phase method is good in predicting what you are looking for. So just as a summary, in this slide, we can see what in short is your process flow. So the important piece is to define parameter and variables, and I would add also being very conscious of your constraints and range of interest, as from those depends the interaction and the time of your optimization, the way to look into your results, and how much time you look into you need to look into your results to get the optimum you're looking for. And also this mid block, it's really the ground base on top of which you can use statistical and response phase method to get additional information. Something to think about when you look in this from a CFD computational is also I have indicated here the cluster use. With these, I actually intend how much computational time you have available, and the cluster is one of the solutions to support optimization that include, for example, transient analysis, but also the interaction with other disciplines. Within this presentation, I will only take care about aerodynamic piece, but you can extend that adding, for example, interaction with the stress analysis or modal analysis, or as I mentioned before, cost analysis. So let's start looking into optimization. This is a typical screenshot of Mode Frontier. Each of these principal icons that you see here are called nodes, and this is the process flow followed from on the very left, you can see algorithm chosen, and then we have here the nodes that represent concept and RIC tool that is integrated into Mode Frontier and that are using in this example to vary geometry. Then we have an ANSYS node that I use to run CFX. And in this particular case, the remaining of the nodes are the interaction with the cluster and then the exporting of data with the cluster. And this is a very easy process, as I'm just going to maximize efficiency. Few things why I call it single process, because I use Mode Frontier workflow to integrate all the aspects of the design I'm interested in. And here it's a single stage, so I'm looking into an impeller diffuser interaction, and I'm looking to some geometrical aspect and some physical aspect, all in the same process. But I'm also use what I call dual processes. In this specific case, I'm going to have two Mode Frontier modules. The one that I call the main module, that's the one that really govern the entire system, where I decided to set which are my physical quantities that govern the problem, and I'm going to define my objective. So I like to reduce the power. In this specific case presented here, this is the two stages that we were seeing before. So I like to reduce the power from that system. And then I built another Mode Frontier module that I call Mode Frontier subsystem, where it's going to take care about geometrical quantities. So inside here, I have two stages, the two stages we have seen before that collapse into a single ANSYS CFX to get then the final output. And then I can have the two processes running in series or running only the geometrical one, and then eventually running only the main module. Now, this is from the process. Let's go see some of the result. When we go doing an optimization, the first piece on the very left side here with this arrow, it's the choice of the optimizer, and I'm not going optimizer algorithm, and I'm not going to spend a word here as there are so many algorithms that you can use, and that really depends on the kind of optimization, number of variables, or number of parameters that you are taking care. But I would like to focus on some of the things you can do once your optimization is done. The first thing is to looking into results. What I'm presenting here, it's a screenshot of the single stage that we were seeing before. We evaluated with an algorithm that is called MOGA2, 54 designs, and it took for me 4.5 days running over a 32 core machine, and each single piece was running in about a couple of hours. Here you do not see the 54 full results. That's just an extraction also to make this slide more readable. But with the result, you can take it, elaborate, and go looking for certain things. What I did at that point, as I want to improve the efficiency of the machine, I went through modifying for this only for the diffuser. And here what it is, what I was saying before. You can segment your design. So the first step I did was to take the impeller diffuser geometry, coupled together, running together, but going to optimize at this point only the diffuser. So I was looking into the diffuser angle, the diffuser leading edge, trailing edge ratio. But the interesting point is that for each of them, I was also calculating the pressure ratio. And in the circle, you can see where are the area where I do find that my results have the most importance for me, as I was designing a machine with roughly 2.3 pressure ratio. And then you can put together and start looking into these results and try to identify how to correlate each other. One of the ways to do this is to use the optimization, the statistical analysis. The slide you see here is referring to the same case where I'm just showing on top of the diffuser also the IGV. As for that stage, we also consider an IGV. And I was trying to understand the correlation between the pieces. The statistical analysis is something that I typically use when I do not have necessarily an idea at the early stage of the design of which are really the critical design components for the goal that I have. But where I would like to spend a little bit more word is about the response surface method. And I'm going to look into that for the two stages case that I was also showing. So where I have the two stages with the CFX flow that we have considered with no multi-point and no transient. I was just considering the design point CFX analysis. So here the thing, if I would like to explore the entire process flow that I have seen, I ended up with 1,665 design cases to cover the space. And considering that a single CFD for that specific case was running in 5 hours over 32 cores, I would have to run for exploring the entire design space in 347 days. But if I run least number of cases up front, as I said, RSM needs a good database. So let's say that I run 20, 30 cases, 35, or if I have test data available, that was not the case as it was in the specific new design. The RSM runtime is only 2 minutes and 5.5 seconds. That's why I said originally it's important that if you want to use this technique, you know exactly what you need to calculate and how you set up your problem. As you do a mistake, the RSM, it really do the mistake too. How can I use it, and which are the benefits of it? First of all, if you are in early design stage, you can have a quicker look at the optimization direction. As with the RSM, you can really decide to explore the full design space if you do not have an idea of where your design space best fits. But on the other side, you can also investigate some of the particular area of the design space to get some interesting information. And that's what I would like to show now. So first use. Here you can see the amount of cases run, so the 1,665, plotted versus the pressure output at stage 2. Why looking into that? We have a 2 stages machine, and one of the idea was, I know that my machine will surge, and you typically look for surge only at the design point, but we had a broader ambition. And so as we are also using IGV, we were also trying to investigate where and how we can detect analytically the surge point with more than one condition. So what this graph told us was that there may be some cases that are wrong in terms of RSM analysis, so you do not necessarily believe too much, but it also gives you an indication on which area you can get more likely a surge in extreme condition. You have to think that between the parameters that we use to run this RMS, there are also pressure and temperature on top of IGV angle variation. So you can select which point you are interested in and maybe running transient analysis for a few cases only. So that's one of the uses. Another possible use is the characterization of a component. In this particular slide, still for the same case as before, we are looking into the characterization of behavior of the IGV valve in the full space. So on the top left graph, you see how many points for how many different IGVs angles are included in these 1,665 cases. And actually, the more interesting piece is the graph that you have at the bottom, as you can extract from the data a correlation chart that tells you flow, power, and IGV angle, how they are correlated each other, and can give you an idea, for example, of where you have to concentrate your design effort in reducing, for example, inlet pressure drop, or which are the cases that are more delicate. So which are the cases where you're not going to spend any effort in making the optimization of your design. And you can do this with any component. So with the same analysis, you get more than one opportunity. We get the surge or choke characterization. We can characterize a single component to get details. And last, you can also get some component maps. Again, here it's not reported the entire 1,600 configuration, as otherwise the graphs will not be clear, but I have extracted information. Two kinds of different information. From one side, I have plotted for some flow range of interest the pressure of the stage or at the exit of the machine and see how they vary under certain condition to verify if I have a uniform flow pressure field or not. Or another way is to, within the 2 stages of design, you still have the information per each single stage. So you can extract the information of what happens if you change some of the parameter within the single stage. And in particular, this graph here was done searching the best speed for the design, as we were also varying speed to look for the best aerodynamic speed at our condition. And I was also looking, depending on the speed, which is the choke area, so where I can't expand my design. So following to that, there was a discussion on what is the best speed. And all of that was just coming out of a single analysis early stage in the design, so that after that I can really decide which direction to take in continuing the development. And with that, I think I have finished a very quick overview of the optimization process that you can use, and I don't know if there are any questions. So if there are no any other questions, I think I can pass it over to the next.
Okay, no, we have no question. Thank you. There is the turn of Eric Mazzoleni.
Okay, hello everybody. Okay, with my presentation, I will give you a quick overview of the system simulation, so the way how we can pass to the 3D analysis of a pump, of a compressor, to a system analysis, and so to find a way to combine and having a general view of the problem when you have the design of your pump. So the idea in this kind of simulation is to, generally speaking, is to reduce the pressure drops and avoid the water hammer effect in these systems. And you can do it using 1D simulation approach. This is Flownex is a 1D tool, so it's a 1D CFD software. And it's based on conservation of mass, momentum, and energy. And the idea is that you have a network, and your pump or your turbine is a part of this network. So it's a component, and we can see how we can put the information about these components inside your network. And the idea is to have a look, as I said, at the entire system where the pump is located. So the idea is that you have a real plant, you have a P&ID scheme, and then you have your Flownex model that is one-to-one to your P&ID, and you can simulate transient analysis. That's what is generally done in 1D CFD, because it's a really quick model, the 1D, so the Flownex model, so you can run it in a few seconds and having the results about your transient simulation. So now we will have a look in a couple of examples of approaches when you have pumps to be designed and to be simulated inside a 1D system. So the first example is a fire suppressor system. So here the problem is to reduce the pressure peak, so the water hammer effect that is observed during the startup of the pump. And the other problem is to avoid the trip of the pump. So when you have a rapid startup of the pump, you can have a lower pressure in the intake section of the pump. So this is the Flownex model. So you have the water tank. Here you have the three pumps in parallel, and then you have all the network with all the orifices, so all the sprinklers that are used to spread out the water, so the nozzles. And the idea is the simulation of the startup of this system. So you have a curve that is regulating the RPM of the pump over the time. And if this regulation is not done correctly, so if the pump is ramping up to the 3000 RPM too rapidly. So in this case, in 1 second, 0.8 seconds, you have a peak of pressure, and at the same time, so this is the water armor effect. So at the same time, you have cavitation. So at the intake part of the system, you have a pressure that is below the saturation pressure of the water. So you have cavitation. So that's why you have to avoid this situation. So both the pressure peak and the lowest pressure in the intake manifold. This can be done in different way. For example, using a motor with a low startup torque, so you can control better the velocity of the ramp up of the RPM of the pump. Add the flywheel to the shaft to have a slow transient, or use a star delta starting. So it's a way to control better the current of the motor and have a slow startup of the pump. These are the results using these countermeasures, and in this case you can see that the startup is lower, so in 2 seconds. And here you have also the example of the star delta switching mode for the pump, and here you can see that the peak of the pressure are reduced, and also you no more have any cavitation. So this is the way how you can have a look at your pump when it's placed in the entire system, and try to avoid this problem and having direct influence on the way how you can control the motor and the pump startup. Okay, we can now have a look at another example. So the a line slurry system redesign. So in this case, you have a slurry flow. So slurry flows are flow when you have, for example, water with lime in this case. So you have particles so inside the water, and you have to design this kind of slurry flow. And this system is generally associated to the increased pressure, delivery pressure. So you have to design correctly the pump that has to be placed to run this system. And the other problem of this system is for sure not to block any duct, and try to having a correct flow, let's say, and a constant moving flow, and avoiding any deposition inside the ducts. This can be done placing the particle size distribution, and for sure the pump pressure head, so the pump characteristics inside Flownex. The main results that you can obtain from this kind of simulation is 2 parameters that are post-processed by Flownex, which is the position velocity, which is the red curve, the position velocity versus diameter, and the other curve is the lime slurry velocity versus diameter. So you have the mean velocity inside the pipes according to the diameter, and you have also another aspect, which is the deposition velocity. So the idea is that if you select a specific pipe, you could have an higher deposition velocity, which means that you could have blocked your pipe. So if this velocity is deposition velocity is too high, your pipe could be blocked, and at the meantime
also the line slurry velocity should not be too low. So the mean velocity, so the velocity of the mixture between water and particles should be high enough to have a continuous flux and transportation of the line. So the idea is to have a redesign. So you are at this point of the diameter, and you would like to go to 100 millimeter of the new pipeline diameter, and so you are moving in a more safety region in terms of deposition velocity and line slurry velocity, which are higher, and deposition is lower than the previous simulation. Going this way, for sure, you have also to redesign your pump because you have an increase of pressure drops. So basically, you have to make a simulation about the characteristics curves, so the pressure drops of your system, which is these red curves, so the system resistance curves. And here you have different pump head pressure head, so you can select now a better pump that is more reliable and can provide can work in an efficient way according to this new system curve. For sure, you can also make some consideration about the efficiency curves and also have any idea of energy consumption, also selecting the new pump. So in this case, the results is the power consumption can be calculated, and you can select a pump that imply a 3 kilowatt motor need to be replaced. And in this case, you can also have a simulation and also an idea about the using of different pumps, so the design of the efficiency that you need when you have also complex fluids, so not only water, but also, for example, in this case, a mixture of particle and water. Okay, now I would like to show you something that is linked to the previous presentation. So something when you have optimized your 3D pump, you can also use all the parameters that you have to make a co-simulation between a 3D pump and a 1D simulation. So the idea is to start from the 3D analysis and find a way not only to transfer the information, so not only some performance curves, but having some complex parameters in a surface of response, and to transfer the surface of response in a 1D component. So the idea why we have to co-simulate, because we have to having a very quick response and using the 1D fast resolution to have a general fast simulation when a co-simulation is possible, and without waiting the time of a 3D analysis. So now we will see how we can do it. So the interface from an informatic point of view is the functional mockup interface, which is a standard that is used to make co-simulation, and you can use what is the ANSYS ROM builder, so the reduced order model. So basically, you run several times your 3D model to construct a surface of response that can be compressed in one FMU file, and this FMU file is like a black box and become a new component inside Flownex. So the idea is you have run several simulations. You have surface of response about your pumps that could depend from several parameters, and this performance curve that is not a curve but is a surface of response that depends on several parameters becomes an FMU files, and with the FMU interface can be linked to a component inside Flonex. This is useful for have a co-simulation when you would like to take into account all the parameters that you have used to create and optimize your pump, and also put this information inside the complete network to have some idea about how your pump behave in a real system. So the idea in this case is to use reduced order models, provided which is a way to create this surface of response provided by ANSYS, and using the functional mockup interface, which is just an informatic way to compress all this information in a unique black box. And all this work is done before to create a surface of response and 3D simulation. But at the end, you have just one file can run really quickly, and can be linked to a single component in Flonex to have a real digital twin, so a model that can run really quickly, and you have computational time that are not big effort, so you have lower computational time. So the idea is that you have a digital twin with your pump that you have designed, and the real system where the pump will be placed. Okay, so I think it's everything from my side. If you have any questions about system simulation and about Flonex and how to make this kind of co-simulation, you can contact me. I'm Eric Mazzonini from EngineSoft, and this is my email. Thank you, everybody, for following these presentations, and I leave time for questions for me and or for all the other speakers.